Hello everyone, myself Ashish Desai, Assistant Professor, Mechanical Department. Today we are going to discuss here unit number 5, type of flow. So this is section number 2. So in that content we are going to discuss here the flow of viscous fluid between two parallel plates. So already we discussed regarding the flow of viscous fluid between the circular pipe. Now we are discussing regarding for two parallel plates. So for flow of viscous fluid between two parallel plates, so here we considering the shear distribution, velocity distribution, and the ratio of maximum velocity to average velocity and difference of pressure head for given length of parallel plates are to be calculated. So these are the data we are calculated from the parallel plates, and we are deriving these relations for shear distribution, velocity distribution, ratio of maximum velocity to average velocity, and difference of pressure head for a given length of parallel plates, which are calculated. So first of all, we will discuss regarding this diagram. So here we considering the two plates, which is separated by distance t. So this is the first plate over here, second plate, and this is separated by distance t. So here I mentioned. So here we are considering the smallest element. So that smallest element having the length. So length is about delta x. So actually this is fluid element A, B, C, D, and BC is a elemental length, that is delta x. So here I draw a delta x, and here the vertical distance is about delta y, and this is the distance t, and this smallest element is apart from the distance y. That means this parallel plate is above of this smallest element, that is y. So now we applying the pressure forces over here. So suppose we considering the pressure force on AB face. So pressure force is nothing but pressure into area. So first of all, we're discussing regarding the pressure force. So here pressure force is nothing but pressure into area. So here we calculate the pressure here into area. So delta y into 1, because this vertical face is delta y and this thickness is 1. So that's why this P is nothing but pressure, delta y into 1, that is nothing but area. 1 is because the smallest element length is, sorry, width is 1. So I consider here 1. So that's why P delta y into 1. So this is on face AB. So similarly we consider the opposite force on that side, that is on CD face. So that face becomes P plus dou P by dou x into delta x into delta y into 1. So this is the pressure force actually we are considering over here, because if you consider delta x, so this delta x is 0, what will happen, that CD becomes AB. That means this, there is no gap, that is 0. So if you put the value of 0 over here, what will remain, only P delta y into 1, P delta y into 1. So whenever the change in the distance, that is delta x, is there, that's why we are computing like this: P plus dou P by dou x delta x into bracket delta y into 1. So this is on face CD. Now we considering the shear stress. So here shear stress is along the this parallel plate. So suppose we considering the shear stress at this bottom of the surface, tau into delta x into a 1. Tau means shear stress into this area, because shear the stress is nothing but shear stress into area. The shear stress is tau, delta x into 1 is area, because this delta x is nothing but on face BC, and 1 because 1 is width. So this is the width, tau into delta x into 1. So we put up this here because shear force is acting over here. So in this diagram we consider first on face AB and face CD the pressure force is acting, and force BC and that face CAD the shear stress, or can say shear force, will be acted. So similarly we have to put up on AD surface, because here we are acting tau delta, then dou by dy, then delta y into delta x into 1. So only we have to change the delta y. If you take delta y into 0, that means this width will be 0, that means BC and AD will be same. So if you put this 0, only remain tau delta x into 1. So like this we have to manipulate this equation: tau delta tau into delta y delta y into delta y delta x into 1. So this is the formulations we are considered over here, and the flow is taking from this left to right. So this thickness is that T. Now we go for the real type problem, because we have to find out here velocity distribution, shear distribution, ratio of the that average velocity and maximum velocity. Now we consider first the pressure forces. So already we consider this pressure force on AB, that is P delta Y into 1. P, that is pressure force, is nothing but pressure into area. So for pressure we can consider as P. Area means that length is delta Y, so I can take delta Y. Width is 1, so that's why width is 1. So therefore face AB, the pressure force is P delta Y into 1. Now we consider for pressure force, is it opposite to the AB, that means on the face CD, the pressure force is nothing but pressure. So this pressure plus dou P by dou X into delta X into the bracket delta Y into 1. So here we put the value of this delta X, so that length is delta X 0. What happens 0 means only remain P delta Y into 1, because delta X, if you put 0, only remain P delta Y into 1. That means if you take opposite of that, this depending on your length, that BC. So the next equation number 3, the shear force is acting on the BC face. So that shear force is nothing but shear stress into area. So shear stress is nothing but tau, and area is nothing but that face BC, that is delta X, and width is 1. So that's why delta X into 1. So this is about face CBC. Similarly, we apply for face AD. So that becomes tau plus in the bracket tau plus dou tau by dou y into delta y into the bracket complete delta x into 1. So this is only change delta y. We can, if you put 0, what will happen? Only that remains tau delta x into 1. Tau delta x into 1. That means if you take if you neglect this distance delta y, then this AD and PC will be 0. So here we have considering delta y, that's why it is separated, and that's why the equation become like this. So these are 4 equations we require for the formulation for velocity distribution, shear distribution, then finding out the ratio for average velocity to maximum velocity, and also we have to find out the pressure drop over the length. Now we have to take resultant force in the direction of flow is 0. So here this P delta Y into 1, so P delta into Y into 1, if you take positive, then this force, that is P plus dou P by dou X delta X into delta Y into 1, this force is opposite, that's why I can take minus. Okay, minus. Then next the shear stress. So shear stress on BC we can consider the minus, because this is in opposite manner. So whenever the force is on AB, the shear stress is on base BC. So that's why I can take as a tau delta x into 1. So that's in my negative direction. So negative direction. So this is negative means this force is positive. So I take positive, that tau tau delta y into delta x into 1. So this is the same value we have formulation for resultant force. So if you take this same equation as it is, so after simplification, that means if you take the simplification, so that bracket will be solved. That means P delta y into 1 minus P delta y into delta y into 1 dou P by dou x delta x into delta y into 1 minus then tau delta x into 1 plus tau delta x into 1 tau then delta dy tau delta y into delta x into 1. So these equations, if you take for simplification, after getting the cancellation, only remain the terms, that is minus dou P by dou x into delta x delta y dou tau by dou x into delta x delta y equal to 0. So if you take the dividing delta x delta y, what will happen? Only remain minus dou P by dou x is equal plus dou tau by dou x equal to 0. So that means that dou P by dou x is equal to dou tau by dou y. So this equation is related with respect to pressure per unit length, or you can say the distance, that horizontal distance is equal to dou tau by dou y. That means shear stress is depending on the that separated distance y. Now take the velocity distribution. So for that we know that tau is equal to mu du by dy, that is Newtonian laws of viscosity. So this tau, what is the value of tau? We can put tau is nothing but mu du by dy. So directly we can put here mu du by dy instead of that. So what will happen? Like this, dou tau by dou y outside, and instead of tau we can write mu du by dy. So after solution we will get the dou P by dou x into dou u by dou y square. and mu is constant term, so we can take outside of this. So now we can take dou tau y by dou y square 1 upon mu dou p by dou x. So this same formulation, that means dou 2y by dou y square is equal to 1 upon mu dou p by dou x. So same equation we can utilize and integrating the above equation with respect to y. So if you take integration on both sides, so first of all, this dou 2y by dou y square becomes dou y by dou y plus 1 mu as it is, dou p by dou x as it is, into y plus c1. So this is the integration for this equation. After once again we can take that dou p by dou x is constant, and once again we can integrate it here. So what will happen? Dou u by dou y, that becomes u. So u is equal to 1 upon mu as it is, dou p by dou x as it is, y square, because we have to integrate with to y, that's why y square by 2 plus c1y plus c2. So this is the final equation for the finding out the general form of velocity distribution. Now we know that we can put the values of boundary conditions. So for putting boundary conditions, y equal to 0 and u equal to 0. Second, y equal to t and u is equal to 0. What is meaning of that? Y means that separate distance. Okay. Suppose this is 0 means velocity also 0. And if you take when velocity is 0, when y is equal to t, so that separate distance is that maximum, and that time the wall velocities become 0. So this is about the boundary condition. Now we put the boundary condition first, that is y equal to 0 is equal to 0 in equation number 2. So we can put this equation number 2, and this is also we can put in the equation number 2. So first of all we look at this for y equal to 0 equal to 0. So here we can put this, and after that we give the value of c2. So c2 is becomes 0. Now we know that y equal to t is equal to t is that u equal to 0. If you put this equation in a general format, what will happen? This like equation becomes 0 1 my mu dou by dou x t square by 2 plus c1 t plus 0. So for formulation, c1 is equal to minus 1 upon 2 mu dou p by dou x into t. So this is the equation for c1 c2. So this c1 c2 we are putting into the equation number 2. So that means c1 and c2 we can substitute directly equation number 2. So that becomes 1 upon 2 mu dou p by dou x y square by 2 plus c1 y plus c2. This is equation number that previous one, that is 1. So if you put the value of c2 equal to 0 and c1 is a value that is minus 1 upon 2 mu dou p by dou x into t. So if you put this value, what will happen? That equation will separate out, and then finalize the equation, that is u is equal to 1 minus 1 upon 2 mu dou p by dou x into the bracket ty minus y square. So this is the equation. This is general form of equation, that is equation number 3. Okay. So in above equation, mu dou p by dou x and t are constant. So these are the term constants we are considered over here. Now this velocity distribution across the plate is parabolic, because velocity is at the wall of the side is max, that wall of the sides velocity is 0, and is at the center point the velocity is maximum. So here we can clearly mention why umax is maximum, because the parabolic that approach is there, because maximum velocity is at that center and 0 velocity at the wall sides. So this approach we have to keep here, that's why this curve is parabolic. Now we can take as it is the equation number 3, sorry 3, right? This is general form of equation. That equation becomes u is equal to minus 1 upon 2 mu dou p by dou x ty minus y square. Now we put this is equation number 3. Now we put the value of t. So t means what? At the center of the point, suppose your distance is t, so that is separate distance t. When it is maximum velocity, it is at center, so that distance separated by t is there. So if you take the distance t by 2, so this becomes y equal to t by 2. So if you take view y is equal to t by 2, what will happen? After solving this, ty minus y square. Okay, so this is the equation. If you put the value of y t by 2, then after putting this value, we will get the value of u max, that is 1 minus 1 upon 2 mu dou p by dou x t square by 4. So this is the equation for u max, maximum velocity. So this is maximum velocity. Now we calculate for average velocity. This is equation number 3 is called as general form of velocity. Equation number this is called as that u max, that is maximum velocity, and after that we will get the average velocity. Okay, now we move for the rate of flow through the stream. So we know that dq is nothing but velocity into that area of stream. So if you take the velocity as it is and area of stream, that is dy into 1, because dy is that particular that height and width is 1. So after putting the velocity at distance y, so here we can put velocity at distance y means what? We put up the value of that in general form equation, that is velocity, and area is dy into 1. So after we have to integrating with 0 to 1. So after integration, if you take the constant term as at it is, that is 1 minus 1 upon 2 mu dou p by dou x is constant, and then only remaining equation is like this. So after that integration, t square, that is y equation, t as it is y square by 2. So here y cube by 3. So this is about the value of q. So after putting the value of this y in, sorry, that y instead of t, so that's why we come t cube by 2 minus t cube by 3. If you take multiplication in cross manner, so 3 into 6, 3 into 2, 6, and 3t cube minus 2t cube means t cube. So this is about discharge. So that q is equal to minus 1 upon 12 mu dou p by dou x into t raised to cube. Now we can take as it is the equation for discharging, and then we go for the average velocity, that is u bar is equal to q upon area. We can put the q as it is and area is t into 1. Okay, so this is regarding the paper. So here we can conclude that the 1 minus, sorry, cancel out t by 2, that is t square and t. So after calculation of that, 1 upon 12 mu dou p by dou x into t square. So this is about average velocity. Now dividing this equation, u max and u bar. So already we calculated the u max, that is maximum velocity, minus 1 upon 8 mu dou p by dou x into t square. So this is your that max velocity, and for u bar, that is average velocity, is minus 1 upon 12 dou p by dou x into t square. So after cancellation of this term, that is only remain 12 by 8, that means 3 by 2. That is the equation. Okay, so this is called as ratio of maximum velocity to the average velocity, that is equal to 3 by 2. Now we move for the finding out the drop of pressure head for given length. Okay, so first of all, we know that the equation, that is u bar is equal to minus 1 upon 12 mu dou p by dou x into t square. So this is the equation for average velocity. So average velocity, we have to already find out this, and this equation we use for the finding out the pressure head. Now we collecting the term, that is manipulating the term, that is dou p by dou x is equal to minus 12 mu u bar t square. So here we have to only crossing this to each other, and then if you plot, if you go for the dou x on that side, so this dou x on that side, and after that we can take integration. So we will get the value of p1 minus, sorry, integrating 2 to 1, and here we can take the integration with 2 to 1, which is pro dx. So here x1 minus x2, and here p1 minus p2. So after putting this value, that is x2 minus x1, so minus sign is here, na? So that minus sign you can take outside of that, then x2 minus x1. So this is the relation. Now we know that x2 minus x1 means what? X2 means what? So this is whole distance x2 and x1. X1 is at section 1, so only remain L. So that's why I can put as a L. So that P1 minus P2, that is nothing but the pressure drop, that is nothing but 12 mu u bar L divided by T square. Now if you find out, this same relation is there, P1 minus P2 12 mu u bar L divided by T square. And if you put the drop of pressure, so that becomes HF is equal to P1 minus P2 by rho g. Now 12 mu u bar L divided by rho g t square. Only we change this P1 minus P2, and rho g we can take as it is. So after putting this value, that becomes HF, that is head loss due to friction, and this friction, or I can say this losses, is major one, and that equation becomes 12 mu u bar L divided by g rho gt square. So this is about the pressure head, or you can say the pressure drop. Now shear stress distribution, that is tau is equal to mu du by dy. So du, so instead of u, for average velocity we can put the value of minus 1 upon 2 mu dou p by dou x ty minus y square. So after putting this value, we will get the finalizing the equations. So after finalizing the equation, the shear distribution is equal to tau is equal to minus half dou p by dou x t minus 2y. So this is about the formulae, and now we move for that shear distribution, that is tau is equal to minus 1 half that dou p by dou x t minus 2y, and if you put the value of y 0, so that equation becomes for maximum velocity is tau is equal to minus half dou p by dou x into t. This is about the maximum stress. Then velocity distribution in general form, that is we can calculate as a u is equal to minus 1 upon 2 mu dou p by dou x into the bracket ty minus y square. Then you can go for ratio of maximum velocity to average velocity. So as we know that the u max upon u bar is equal to 3 by 2. Drop of pressure head for the given length is P1 minus P2 is equal to 12 mu u bar L divided by T square. And if you put the HF drop, then you can say only V divided by rho g, that is P1 minus P2 by rho g, that means HF, that becomes 12 mu bar L rho g T square. And therefore, if you go for shear distribution, this is the general form of equation. If you put the value of the y0, that is shear distribution, is maximum, so that becomes tau naught minus half dou p by dou x into t. So this is the general form of equation. Now we move for the next stage. So that is regarding the problem. So already we discussed in a formula basis. Now we go for final equation, that is pressure. So first of all, we calculate the pressure gradient, then second average velocity, and third discharge for a oil of viscosity 0.02 Newton second per meter square. The flowing between two parallel plates 1 meter wide maintained at 10 mm apart, and the velocity midway between the plate is 2 meter per second. So first of all, we find out the given data here. The viscosity, that is the mu 0.02 Newton second per meter square. So that is your dynamic viscosity. So already here mentioned, that is oil of viscosity 0.02 Newton second per meter square. Then width is about 1 meter, because already mentioned the parallel plates 1 meter wide. So that means B is 1 meter, and the distance between the two plates is about 10 mm. So 10 mm is there, and the velocity midway is between the plates u max is equal to 2 meter per second. So this is velocity midway. Okay, now we move for first point, that is pressure gradient. So if you know that u max, that is 1 is 1 upon 8 mu dou p by dou x into d square. So after putting this value, u max is known to you 1 upon 8 mu, that is 8 into 0.2 dou p by dou x we can take as it is, and t square, that is you can put the value of t over here. Now after getting this value, dou p by dou x is equal to minus 2 into 8 into 0.02 divided by 0.02 into 0.01. So if you put this, we will get the value of dou p by dou x, that is minus 3200 per meter. So this is about the pressure gradient. And now we move for average velocity. So as we know that the average velocity for finding out the u max upon u bar is equal to 3 by 2. Now we put the value of u bar is equal to 2 mu max upon u, there were 3. After putting this the value of u max, that is 2, and 2 divided by 3, that is 1.33, that is average velocity. Now discharge. So how to find out discharge? So actually you know that q into u bar. Now Vt as it is, that is area, into u bar is their uniform velocity, 1 into 0.1 into 1.33, that is from u bar. So here u bar already mentioned, and then after putting this value, q is equal to 0.0133 meter cube per second. So this is all about the problem. So here already we discussed regarding the flow viscous between two parallel plates. So in that content we are already discussed about the pressure distribution, then shear distribution, then all type of that discharge. So this type of uh, we have studied in this lecture. uh, so this is about all data.